A final word now about complexity. We have proved that the model checking problem is decidable, but how computationally expensive is it in terms of time and space? It is not hard to see that the construction of the automaton associated to a formula can be done in time and space that grow exponentially with the size of the formula. In fact, the size of the result itself, the produced automaton, is also exponential, since its states are sets of formulas. Moreover, the construction of the product between an LTS with a state and an automaton takes time and space, growing linearly with the product of the sizes of the two components. Finally, if we are a bit careful, in particular, apply an efficient algorithm such as Targent's for determining the strongly connected components of the underlying graph, we can decide emptiness of an automaton, of an automaton's language in time and space linear on its size. And of course, keep in mind that in these lectures on LTL model checking, by automaton, I always mean GNBA, generalized non-deterministic Buki automaton. So the discussed complexity bound refers to them. Putting all these together, we get this overall complexity of the model checking problem. Time and space growing linearly with the size of the LTS and exponentially with the size of the formula. Interestingly, since in practice we have small LTL formulas and large LTSs, the linear growth with the size of the LTS is more of an efficiency problem than the exponential growth with the size of the formula. This concludes my lectures on LTL model checking, and here's a summary of what we discussed. We formulated the model checking problem for LTL, then introduced GNBAs, and discussed their accepted languages consisting of infinite words. We showed how to translate LTL formulas into GNBAs and how to construct the product between label transition systems and GNBAs. We showed how to decide the emptiness problem for the language accepted by GNBAs. These were combined to produce a three-step solution to the LTL model checking problem. Finally, we mentioned briefly some time and space complexity issues of the model checking algorithm. As you could probably notice, these lectures and these slides are aiming to be essentially self-contained, but still much more details and more context are given in section 5.2 of Bayer and Catton's monograph. Also, what I've discussed in these lectures is a rigorous and detailed but fairly basic introduction to this problem. There's been a huge amount of research on designing more efficient algorithms using techniques such as symbolic representations of the automata states or taking advantage of certain specific forms of LTL formulas. These two papers by Moshe Vardi are a useful point of entry if you want to read about research on this subject.